Hello, this is Chapter 2, Section 8, Algebra 2, Graphing Linear and Absolute Value Inequalities. And FYI, it's also the last section of the chapter, so obviously that means exam coming up. Anywho, try to ignore my hair. It's kind of going crazy right now, but anywho, wanted to show you how to graph linear and absolute value inequalities. Good news is that graphing linear and absolute value equations we've already done, and so that part of the lesson today is the same, but there are some unique differences between graphing equations and graphing inequalities. And so what I've put here on the board is primarily what those differences are. When you graph an inequality, you are either going to be graphing what they call a boundary. It could be a boundary line or a boundary V. Because obviously absolute value is always the shape of a V. It could be a boundary parabola. So we call that, the actual equation itself is a boundary. And that boundary can be either solid or it could be dashed or what they call broken. So basically when you draw a number line, when you're graphing inequalities on a number line, it's kind of like the equivalent of having an open dot versus a closed or solid dot. So if, and these are actually backwards, I'm so sorry. I hope you haven't written that down yet. So let me fix this for you real quick. So basically, whenever you have the equal to, greater than or equal to, we know that the equal to means that it includes the point. In this case, it includes the line. So therefore, we have a solid boundary line, or boundary curve, if you will. If you have a strictly greater than or less than, which means that it's not equal to, so it doesn't include the actual point, or in this case it doesn't include the boundary, then you have this dashed or broken boundary line. Okay, so that's one difference. And then of course when you also shade on a number line, greater than or less than, if it's greater than you're going to shade to the right, if it's less than you shade to the left, and so on and so forth. So there's also shading to do when you're graphing in 2 dimensions. And so what you're going to be looking at is anytime that it's a greater than, or if it's a greater than or equal to, either one of these cases, you're going to be shading above the boundary. And if it's less than, or if it's less than or equal to, you'll be shading below the boundary. So that's important to know, but of course I will show you how to do that with some examples, especially where the shading comes into play, because sometimes the less than or greater than can be deceiving when there's negatives involved. But there is a fail-proof way to know which side of the boundary line to graph. So I will be showing you that as well. So here we have an example. It says graph y greater than negative 3x minus 2. And so kind of sort of as a quick little recap, we know from previous lessons this is y equals mx plus b. And when you have it in mx plus b, there is a y-intercept, which in this case is 0, negative 2. Based on this number here, and then we know that the slope is the number in front of x, which in this case is negative 3. So based on that information, graphing this should be totally normal. You will notice that this is a greater than symbol, and as we said before, greater than, it has no equal to, means that we're going to be using a dashed boundary line. So well, first I'll plot those points here. So here's my 0, negative 2. There is my y-intercept. And my slope is negative 3. And so if I want to make that into a fraction, it means negative 3 over 1. So that we talked about that before. So that means I'm going to go down 1, down 2, down 3 units, and then to the right 1 unit. And that's where my second point will be. And then when I connect them together, I don't connect them with the solid line. I'm going to connect them 1, 2, 3 over 1 this way. I'm going to connect them with a broken line. So there goes, try to get that lined up right. So there goes my graph. So the only part that's left now is the shading. Now according to what we said earlier, it's greater than, so we want to shade above. Now, I don't know how many of you can actually tell just by looking at it that above doesn't really mean like above. I mean, I think of above, I think up here, I think below, I think down here, but this line is not really like above and below, it's more like left to right. So sometimes it can get confusing, especially when I look at this graph. I'm really close to the origin here. So, and there are times when you will graph the line, and because your graph is just slightly off, you might not get it to cross in the exact spot. So it is a very good way to check your work. Again, I do think that graphing above is going to be graphing this side, but if I want to confirm that, I can do that very easily by doing this little test, and I like to call it the lie detector test. We know that in real life, you know, when you want to know if someone's telling the truth, you can give them a little test. And if they fail that test, well, then they're lying, right? So that's kind of the idea. So we want to do something similar here. And what you do is, provided the line is not crossing through the origin, which in this case it's not, then the lie detector test is 0, 0, the origin. We basically want to plug in x and y equal to 0 into our original equation to see if it's a true statement or a false statement. If it's a true statement, then we're going to shade the side of the line that has the origin in it. If it's a false statement, then we're going to shade away from the origin, if that makes sense. So, for example, here we have 0, 0. So I'm going to replace y with 0, greater than -3. I'm going to replace x also with 0, -2, and see what happens. So here over here we have a 0. We know that -3 times 0 is still 0, and 0 minus 2 is -2. So here's the statement. Is 0 bigger than -2? The answer is yes, because 0 is bigger than any negative number. Okay, 0 is always bigger than any negative number. So this is true. So here is my origin. And since this point gave us a true statement, it means that we are going to shade toward the truth value. Okay, now if this had been a false statement, if this had come to be false, then we would shade on this side. But because it's true, we're going to shade where the origin falls. All right, and I'm going to show you how to do that here really quick like. You can obviously use your pencil, but I don't have a pencil, so I have to use this funky little highlighter. And it is kind of crazy here, so we're going to shade this side. You want to try to cover as much of your graph as you can. It doesn't have to be perfect, but it should be a region, a whole area of space that is shaded. All right, and that is how you graph that little guy. We're going to do one more for you here. This graph was in y equals mx plus b. That was the form that it was in, and so we used the y-intercept and we used the slope to graph it. This guy is actually in what we call standard form, and I hope that you remember that with standard form, you want to graph by using x and y intercepts. So in this case, we are not going to graph this by using y equals mx plus b because it's not in y equals mx plus b. This is the one where we use hide and divide, or basically you find the x-intercept. So to find the x-intercept, you force y to be 0. If y is 0, then 4 times 0 is just going to be 0, and this whole term will go away, and you'll get x equals 2. So if x is 2, y is 0, that's your x-intercept. All right? Now for your y-intercept, you do the opposite. For the y-intercept, you make x 0. So if I make x 0, then what I have is I hide the x term, and I get 4y greater than 2. If I divide by 4, hence why it's called hide and divide, then y, remember x was 0, then y will equal 2 divided by 4, which is 1/2. Okay? So remember that when you are graphing something that's in standard form, you want to use the x-intercept, y-intercept method. And so we're going to plot those 2 points, x 2, 0. So here's going to be 2, 0, x is 2, y is 0 right there, which makes sense. It's the x-intercept, so it should cross the x-axis. The y-intercept is 0, 1/2. So 0, 1/2 is right about here, right in between 0 and 1 for the y. Okay, and again, this time my line is going to be broken because it's a greater than. So we are going to draw that little guy. And there we go. Now this graph is probably pretty easy to tell that above is over here and below is here. And it does say above. But again, just to be consistent, I am going to test the origin to make sure. So I'm going to get 0 plus 4 times 0 greater than 2. Now remember that when we test the origin, we replace both the x-coordinate and the y-coordinate with 0 in the original inequality. So 0 is obviously 0, 4 times 0 is obviously 0, so 0 plus 2, so we get 0 is bigger than 2. So in this case, we are saying that 0 is larger than 2, which is not true. We said earlier that 0 is larger than any negative number, but 0 is not larger than a positive number. So this is false. Okay, now because it's false and the origin is right here, the origin lies below the boundary line. Therefore, we're not going to shade where the origin is. We're going to shade away from the origin because it wasn't true. So we're going to shade over here. Now again, we probably could have figured that out just by looking at the symbol greater than in this case because the graph was more flattened. But it's always nice to be able to have a way of checking just in case you're not sure. And it doesn't take very long to check. So there you go. That is how you solve or how you graph an inequality that's in standard form. So now we're going to give you a chance to graph these two inequalities, and then we're going to move on. What we saw in the past two examples is that we had examples where we were using both of them had broken or dashed boundary lines. In this case, we're going to end up with a solid boundary line. That's one difference in this example. The second difference is that it's a word problem. So hopefully we can kill two birds with one stone here. So let's read what this little problem tells us. A recreation center offers various 30-minute and 60-minute art classes. The recreation director has allotted up to 20 hours per week for art classes. In part A, it wants us to write an inequality to represent the number of classes that can be offered per week. Graph the inequality. All right, so what we want to do is convert this to maybe like hours here, because it says here that talks about up to 20 hours, how many classes can be offered per week, but we're doing hours here. So we want to convert our 30 minutes here to maybe a half hour, and 60 minutes is basically 1 hour. Okay, so what we want to do is we want to have some variables that are defined. So we will say that X represents the half-hour classes. Let's see here. So X is 30-minute class, and then Y will be the 60-minute class. So we want to define our variables. And also the other thing that's pretty important to keep in mind here is the up to 20 hours, because that's going to tell us whether or not we should be using a less than, a greater than, or even an equal to. If it says up to 20 hours, it means that he doesn't want to go beyond 20 hours. So 20 hours is his max. So if it's his max, then we want it to stay less than or equal to 20 hours. So this is telling us that our inequality will be less than or equal to 20. It can be less than 20, it can equal 20, but we definitely don't want to go beyond 20. So to write our equation, it'll be very simple. We're going to take our 30-minute classes, which are basically going to occupy half an hour. So each class, so this is the number of 30-minute classes, number of 60-minute classes. So each 30-minute class is going to occupy half an hour. So we're going to say 1/2 times X plus 1 times Y less than or equal to 20. Okay? So what I'm saying here is that X is the number of classes. So if I have 5 classes, for example, or let's make it easier, if I have 6 classes that are 30 minutes long, that's going to be 6 times a half hour, which is going to be 3 hours worth of time. If I have 12 one-hour classes, then that's going to be 12 times 1 hour, which is 12 hours of my time. So combined, that would be 15 hours of time, which would fall within the less than or equal to 20. So that's kind of where our equation is coming from. But also we want to graph this equation. And because this is in standard form, I'm going to use a standard form technique. So over here, I have like very limited space here, but over here my x-intercept is that I make y 0. If you remember that, okay, I'm going to make y 0. And then I'm going to have 1/2 x equal to 20. So then I divide by 1/2. 20 divided by 1/2 is the same thing as 20 times 2, which is 40. So I get 40, 0 there. For my y-intercept, I'm going to make x 0. And if x is 0, then I'm just going to get y equals 20. So I'm going to come over here to my graph. And here is x is 0, y, I'm doing the y-intercept first. X is 0, y is 20. That is the y-intercept. And my x-intercept is 40. So 35, 40 over here. And then because this is an equal to, we're going to keep it at a very solid boundary line. We're not going to make it a broken line this time. So there we go. And then we need our shading. Again, because it's less than, that tells us that it's supposed to be below. But just to be safe, we're going to check. And this time, I'm going to check over here the origin. So if I get 1/2 times 0, I'm just checking here, plus 1 times 0. Here's my statement. I'm replacing x and y with 0, so obviously I'm going to get 0 on the left. So is 0 less than or equal to 20? Yes, it is. This is a true statement. And because it's true, we're going to shade toward the origin, which is this piece here. So we're going to shade over here. Now, even beyond that, I'm not even going to shade any of the negative stuff, because for ours, it doesn't make sense in this scenario, this real life scenario. It doesn't make sense for us to shade anything in the negative x area or the negative y area, because that would imply that we had negative numbers of classes, which doesn't make any sense for this problem. So we're going to end up with this little triangle here for our graph. Now, after we've graphed it, that's the first part, part A. Part B says, can the recreation director schedule 25 of the 30-minute classes and 15 of the 60-minute classes during a given week, and explain if he can or can't? And that's a pretty simple thing to explain. If you had 25 30-minute classes, that's the x-coordinate. That means the x-coordinate would be 25. Oops, let's not do that. Let's go back to our pen. 25. 25 of the 30-minute classes means that the x-coordinate would be 25. 15 of the 60-minute classes would mean that the y-coordinate was 15. That's the point we're trying to check. Is this possible? If it were possible, then this point would find itself in our shaded region. If it's not in the shaded region, then it's not possible. So when we look at x25, here's x25, and here's y15, 5, 10, 15. So when those 2 points meet, it's going to meet right about here. And since this solution point is not within the region that we just graphed, then the answer here is no. Alrighty? And that's how you do that, little guys. So now we have an example for you to try. And then we're going to go to our last example, which is absolute value. This lesson was graphing linear and absolute value, so we want to make sure that we also graph an absolute value inequality as well. But a lot of it is the same as before. But here we go anyway. So we just learned in the last section how to deal with this little guy. This is a vertical translation of 4 units down, which would mean that I would go 1, 2, 3, 4 units down, and the whole graph would just move down. So normally we do the whole little V thing, so it would be here. Okay, this is an equal to. There is a greater than or equal to here, which means that I am going to make this a solid boundary V. And I want to remind you that if you're still struggling with graphing the translations just by looking at them, that you should probably come see me, A. But B, there is another way of doing it, we talked about making a t-table. You could do that as well if you'd like. We always want to put the vertex in the middle though, and the vertex always comes from taking what's inside the bars and making it equal 0. In this case, it's really simple because the only thing inside the bars is x. So x equals 0. After that, you can pick -1 and +1, which you always want to pick one point that comes after 0 and one point that comes before 0, preferably the same distance apart, and then plug it in. The absolute value of -1 is +1, and 1 minus 4 is -3. 0 minus 4 is -4, and of course 1 minus 3 again is -3. So when you plot those points, you will notice that at -1 we got 1, 2, 3, 0 is -4, and 1 is -1, -2, -3. So we have the same values of the points here. It's just that with translations you can do it a lot faster. So just want to remind you that you can still use the t-table if you need to, but it is in your best interest to graduate to being able to do it with the shortcut way. So anywho, the last thing we have left for this guy is the shading. And again, above, to me, is very simple. It's up here. Below would be, down here. But just in case you're not sure, you could even think of it as inside the V and outside the V. So if it was a less than, then it would be out here, outside of the V. If it's a greater than, it's going to be inside the V. But maybe you're still not sure about that. But again, the lie detector test will still work for us here. So we're going to put 0 in the place of y, 0 in the place of x, and then see what we get. The absolute value of 0 is obviously 0, and 0 minus 4 is -4. So the question here is 0 bigger than -4? And we said earlier that 0 is bigger than any negative number. So therefore, there's my origin, and because I am shading toward the origin, you basically end up, these arrows are just indicating that we're shading toward the origin, then you're going to end up with the shaded area inside the V. And again, if it had been a less than, you would have ended up shading outside the V. So let's finish this guy up. We're just going to shade inside this V here. And then we're going to give you a chance to do one on your own. And then once you have finished the one on your own, then you will be done for your notes today. So this is the one that you'll be doing on your own. And when you've done that, you have done your notes for today. I will see you in class, and thank you for watching.